Hi, I'd like to talk about mass spectrometry in this video, and the machine come in various sizes and shapes, depends on their use and their sample to be analyzed. As you can see, there's a one coming in a box. It's like twice of a regular desktop computer. This is a little somewhat bigger version of it, and this portion is the metallic portion you saw in the previous model, and here next to it you see a chromatography machine, HPLC, to analyze the mixture sample, and then automatically the separated samples one by one will be injected into the machine through this module, and then each sample, the pure forms, will be analyzed by the mass spec for their molecular weight, and the fragmentation pattern we'll be talking about soon. This is a more serious setup. As you can see, this is huge. It's a semi-particle accelerator. This even allow us to analyze heavy atoms and to find their isotope ratios and stuff like that. The mass spectrometry measures molecular weight, such as this molecule, for example. And not only the whole molecular weight, we can measure the weight of this branch, or if you have a carbon 16 isotope, or say 18 isotope with two more neutrons, we can measure them apart, and we can also see the measurement of this ring alone, in addition to the molecular weight of the whole molecule. So basically we are measuring weight of the whole or the fragmentation. The instrument for the mass spectrometry has some parts. There's some ways of sample introduction. To the machine. Then the machine, most of the parts are under vacuum. So it is connected to the very strong, powerful vacuum machine in order to remove any gas molecules. Because most of the spectrometry, mass spectrometry, is measuring the ionic form of the gas. So the presence of other gas will act as noise for the measurement. Once you introduce the sample to the system, you have ionization part. That's the source of ion. That's what you're generating there. Once the ions are generated in variety of method, you're entering analyzer. That's where you sort things out. Like you saw before, if we introduced this sample and ionize them, it will turn into a gas, ion, and also radical. Then it will start to get fragmented. Break it down there, and so on. So you start off with the whole molecule there, But after you ionizing them, positive radical, after you lose electron in various forms, okay, you lose electron, then this will start to break it down. It will break down into a couple pieces. It could be positive on this, radical there, or and vice versa, or both randomly. And this can be further breaking down this as well. So you're going to end up making a lot of fragmentations. So you need to sort out. Then there will be an ion detector. It's same as like a little unit where the positive ions come into the contact. Then electricity will flow in the proportion to the positive ion because they are taking electrons, and the measurement of the current will be converted to the data. So the data processor will generate spectrum. It'll look like it. As you can see, in this process, we don't use light. So it's not spectroscopy, but it is measuring mass, molecular weight. So mass spectrometry. Unlike IR instrument, mass spectrometry come in very different ways. The techniques for each step could vary so much. So I'm gonna briefly mention what are the methods available for each step, so you can choose wisely for your own sample. So once you have a sample prepared, you can ionize them in the gas form in various ways. One of the first ionization method is EI, electron impact ionization. This is one of the first protocol. We shoot the electron at the sample and then knock out electron, and then we ionize the sample. In order to generate the electron beam, we normally use about 70 volt of the power. This technique is commonly used when you have GC mass. So when gas chromatography is analyzing your gas or solution sample, and then the stream of the vaporized sample go through the mass spec ionization chamber, then you shoot the electron and then ionize them. The next method is FAB, fast atom bombardment. So typically we are using an argon or xenon gas, then we accelerate it in kilovolt level of energy. Then the samples are normally in the matrix, and we hit that matrix embedded sample with the argon or xenon gas and ionize them. The next method is electrospray ionization. We'll have a metallic nozzle, and then we spray sample. Then the nozzle has electricity attached to it, so you can remove electron from your sample and ionize it. So this method is in nature is very often applied in LC, HPLC as a sample injector after separating mixture, then mass spec as a sophisticated detector. That's how the things are set up. And next is MALDI, matrix assisted laser desorption ionization. It's basically you have multiple samples on the little plate with the many wells. Then you blast the sample with a laser and ionize them. And the sample are mixed with other chemicals that can absorb the laser energy better and helping transferring energy to the sample more effectively. This is one of the typical MALDI sample plate. And the MALDI is one of the latest advanced technology, and you may find it in the lab most frequently. And also the MALDI is coming normally with a particular analyzer. So I'm talking about ionization methods, right? And then after you ionizing them, it's gonna fragmented. So you need to sort them out using analyzer. Because of the nature of the MALDI, the analyzer that comes with the MALDI is usually TOP, T-O-P, T-O-F, time of flight. So we'll talk about this now. Here, these are the methods being adopted for mass spec to analyze the ion according to their mass to charge ratio. Magnetic sector is one of the first method developed. So what you have is like actually a tube connected with the voltage in order to neutralize the ion that's not going through the tube. Then you have detector in this end. So your mass, the whole molecule or the fragmented ions will be pushed by oscillating voltage and then going through this tube while the tube is placed in the magnetic field. I'm gonna explain this in more detail, but if you have the charged particle moving in the magnetic field, it is curving. So you can select heavier one, lighter one, not able to go through, but just the proper one that you are aiming to detect at the moment is making through and then go to the detector. Okay, so one of the first type of analyzer. The other one is actually a time of flight. It's pretty simple as well. You have the ion source generating ion, then you're accelerating ions using some plates of oscillating voltage. Plus minus charges will be changing on the metal plate. That makes the ion pushed, and then the ion start to drip. But same amount of the force is given by it, so F is given, but the time, because the distance from the ion source to the detector is fixed, right? So if distance is fixed, if you measure the time for a certain ion reach detector, we can measure the molecular weight. So that simple idea may allow us to measure molecular weight, but we can sort out, right? Heavier one comes to the detector slower, taking longer time. The lighter one reaches faster. So that method of analyzer is called time of flight. Like I said before, time of flight is connected with the MALDI frequently. Then quadruple is most frequently used analyzer for GC mass and the LC mass. These are the probably leading analytical tool for pharmaceutical or medical field. That probably is because of the simplicity, and it works pretty well. And even the high resolution mass spectrum adopt quadruple analyzer. So from the ion source, ionization chamber, you have various ions entering the analyzer. Some of them are the whole molecule and or the fragments, and that means all type of mass coming into the analyzer again, just like them. Now they are facing 4 rods, 1, 2, and then the other one above them, like here above them, here, and the other one behind. Okay, so if you see it from there, you see 4 profiles of 4 rods. They are going this way. So the gas molecules enter here in the middle, and those rods, their charges are changing. It's controlled by the computer. So when particles are also charged, as you change the charge on those 4 rods, you can actually make the ions in the chamber, right, oscillate. Pulled, pushed, oscillate. Depends on their mass, right? The heavy ones will oscillate less. The lighter ones will oscillate more. So depends on their mass. The oscillation changes, okay? So by doing so, you can select some lighter ones. You can have them dephase and allowing only the proper mass can travel through and then reaches the detector. Then you can change the oscillation and you can select other mass that's able to oscillate enough, not too much, so get through. So you can keep changing it, so you can selectively let one mass of ion go through and get detected, and next one is now selected and detected, and so on. So quadruple analyzer, very popular and working pretty good. Then the ion trap is a little advanced type of quadruple. Let me draw it. So this is a simple drawing of the ion trap. In little box here, you have 4 parts where you have the voltage connected, just like a quadruple, but you don't need a long bar. You just need a little cup. Then cool thing about this is you have the ions coming in. So in the cup, the little space there, you can have the heavier ones moving slowly with a small diameter, or you can make them move up and down, whatever direction you want, using those voltages, plus minus poles. You are alternating, and then the lighter ones are buzzing around even with the more variations, right? And then some point you can control a certain mass, can make the right flying path and go through a little puncture and get detected. Those are the ones mostly like lighter ones. So you have certain electric force exerted them and then have them move out, exit first. Then you increase the influence of the electricity. You make the heavier ones moving more and more, and then have them exit. And then you do increase more, and then you let the next heavier one, and so on and so forth. So you can have, you know, the lighter ones, the fragmented ones go out first, and then heavy ones later, and so on. So ideally, you can think of these things for biologists, right? If you want to sequencing the say a protein, you can have fragmented a certain protein segment or a single amino acid get out, and you see what was there, and then you let them fragment more as you have them circulating, and then you wait until you have enough fragmentation, and then you let the next one go out, and sequentially you can lose them. Then using the data, what came out in the order, you might be able to get some sequencing. I mean, some ideal case. So you can see the development of the idea. Little magnetic field making things turn or fly. Where is the fly? Time of flight here. Time of flight here. So fly, or have them oscillate in the rod, long path. Now you have them in the trap. But there, with the Fourier transform mass spectroscopy, mass spectrometry, you are detecting not this sort, but about the same idea though. As they are oscillating and rotating inside, we are detecting the frequency of the ions rotating around. Then the idea is you don't have to have them out. You don't need detector. The detector is actually around here, the trap. So the detector detecting the charge oscillation, just like the photon, the light. So the overall oscillation of the charge, right, electric field, you can Fourier transform to find out the frequencies that present there. And then mathematically, you can calculate the masses that you have in the trap. And for that, you needed a really high uh, magnetic field, like I forgot exact number, but maybe 7 Tesla or something, very high magnetic field. So you needed superconductive magnets. But now they have developed Orbitrap. You don't need such high power of magnet, and you can do same thing. So so much advanced is made here as well. Now we have really excellent equipment in the lab. Not only giving the molecular weight, but you can find out the structures, some aspect of the structures, and the ratio of the isotopes, and being able to analyze a big sample like a protein, not only just gas sample with a molecular weight of couple hundred, but thousands and thousands. Then we can somehow control the fragmentation pattern in a way, and you can do much more things that could have been impossible in like 10 or 15 years ago. And also the advance has made in the resolution and accuracy. So say if you have a water sample from some anthropology field, for example, you can exactly measure the ratio of the hydrogen or deuterium or oxygen 16 or oxygen 18 isotopes. So we can calculate the exact ratio. We can measure exact ratio, so we can calculate exact date. All right, let me briefly go over magnetic sector, how it works, the principle of it. When the ionization chamber, whatever the ion source was, ion spray, MALDI, whatever, right? The molecules first got ionized by losing electron. Then some of them will start to get fragmented. Then many different types of ion comes in. So then the magnetic sector has a certain magnet flowing from bottom to top, for example. Then the tip of the arrow will look like a point, right? And then tail look like a X. So when you read a book, you need to check whether the magnetic field is pointing up or pointing down, okay? So when you have X marks, what they mean is the magnetic field is actually going down. So when the charged particle again is moving in the magnetic field, it's getting force. When it's a positive charge, the force is going this way, okay? When the particle is negative, the force is in opposite direction. Therefore, this charged particle is keep getting F amount of the force as it travels, keeps getting more and more forces, not one time, constant force. Then you know what happened. When there's only one time force given, then it just changed the angle and that's it. But if it's keep given, then it is making a circular motion. So the F that's making this charge curve and eventually making it go in a full circle, right? With a certain diameter. Center says here, and that was R, for example. Then the force given to the object, charged particle, by the magnetic field in conjunction with the speed given by the accelerator of the machine will be this much, like we said in previous videos, okay? Then when the object make a circular motion, the acceleration is this at this velocity. Therefore, we can rewrite the formula this way. Yeah, so there, after canceling the velocity, as you operate the spectrometry, you'll be constantly changing the magnetic field in order to select the mass. And how we do that? Well, the velocity of the ions will be same. It will be set up that way. And then charge, we assume that is +1. And there are cases, where you see ions with up 2 charges, 3 charges, and that complicates the spectrum. Just like the IR, there is variations, and this causes the variation in the mass specs. But it also can serve as analytical tool if you always think of the other way. And also, we know as we change the magnetic field, depends on the mass, the R changes, right? So there are 3 variables, and that's not good for us. So we have to fix one of the variable, in this case R, okay? For the magnetic sector, we are fixing R. And as I explained the analyzer earlier, there are other tools that we don't really fix the variations. So simply speaking, if you fix the R, when you have heavy mass, you need stronger magnetic field to keep the R same. Okay. If you have one type of a magnetic field at a certain time, what happens is that The lighter ones, small mass unit, right? Lighter ones will make a small circle. And the heavy ones will make a big circle. What that means is that the heavy ones fly and then force is given, but because it's a heavy, okay, with the same force at the same speed, right? The acceleration, this direction of acceleration is not as much because it's big mass. So it doesn't curve much, so it goes almost straight, making a big circle. But light ones with a small mass with the same force that's coming from the given magnetic field, same force is given, but the light fragment is going to be affected more and curve much and make a small circle. Okay, keep that in mind. Remember the magnetic sector of the one of the analyzer, and there you have voltage measuring detector when the ions coming through the analyzer. Say you have heavy ones and light ones enter the magnetic sector, and there you have the magnetic field. Then since they are flying, they're getting force because their speed is the same, and at a certain given time machine is giving constant magnetic field, and the charges are all +1, so they're all getting same force, so they are getting same force pushed this way. Okay, but because of the difference in the mass, they have different acceleration this way, so the lighter ones curve more and the heavy ones don't curve as much. So say if the magnetic field given is just enough strength to have the heavy one curve with uh, the radius proper and same as this magnetic sector, then it's gonna curve just right and enter the detector. The machine knows at the time something was detected, the amount of the magnetic field given, and they can calculate the mass. The machine can calculate it. But what happened to the L? Well, the L got much force, acceleration to this direction, so it's curving much and run into the metallic piece, and there you have an electron given to it, and it's getting reduced and it's just disappeared. It's not ion anymore. It cannot bounce back and fly again. It's gonna be just neutral. Then when you want to detect lighter one than the heavier one you just detected, the machine's gonna reduce the magnetic field. Then what happens is, say some heavy ones still there, then the heavy one will have less influence of the weakened magnetic field, so it is going to make a less curve, so it doesn't make this much curve. It is going to run into somewhere here and disappear from the gas phase. However, the lighter one that used to turn a lot due to the strong magnetic field, now it is able to manage through the curve and get detected. Then that weak magnetic field that's made by the machine's able to calculate how much mass you just detected. Okay, that's how it works for the mass machine that has a magnetic sector. But like I said, these days there are more sophisticated analyzer but this gives you idea how mass spec is using electric field, magnetic field, and how to detect the tiny particles molecular weight. So simply speaking, mass spec is like you put sample in the vacuumed box, and then using all kinds of energy source, electron, atom, laser, electricity. You rip off the electron, or you have them charged in a way and then have them fly. Then they fly. While they're flying, you give some force to it using magnetic field or electric field, have them turn, have them oscillate, have them moving back and forth, have them spinning around in a little tiny cup or space, and then you have them make a bigger motion or smaller motion, so you can control which mass is able to reach the detector. Or nowadays, like FT case, you are detecting the frequency of those charged particle that generating electric field oscillation, and you are able to get the frequency of each using Fourier transformation we talked about before. So with this, in next video, I'm going to start talking about mass spectrum. Until then, have a good day.